Gases, they're in the air. They're everywhere. Gases have four main variables. Pressure.
Go.
Volume. Mass. Temperature. It's getting hot in here.
Pressure is defined as the physical force exerted on another object. In equations, P is represented as the variable for pressure.
Volume is defined as the amount of space an object or a substance occupies. Volume is denoted by the variable V. Gases are mostly air and they expand to fill their containers.
Common folk know temperature is heat, but us, certified scientists, know it as the internal kinetic energy of a system. In the ideal gas law, we denote temperature using the variable T and measure it in Kelvin, so it is accurate.
N, or mass, of a gas is expressed in moles. N, and the quantity of the mass of a gas is expressed in moles, and by using Avogadro's number, you can relate moles in mass to the particles in a gas.
Gases are mostly air, so they expand to fill their containers. Therefore, the volume of a gas is equal to the volume of its container. In 1662, an Irish scientist named Robert Boyle discovered something groundbreaking about the connection between pressure and volume of gases.
Boyle's law states that pressure and volume are inversely proportional. As one of the variables goes higher, the other one goes lower. The equation for this is the initial pressure times the initial volume is equal to the final pressure times the final volume. This is Boyle's experiment. In this case, we have a vacuum connected to a solid vacuum space, and we have a plastic bag in here. What we're going to do is we're going to turn that vacuum on and suck up all the air, the gas particles from there. But there's still gas particles inside of here. And when there's no more, these gas particles inside of the bag will try to expand to fill up the empty space. Let's turn it on and see what
Mr.
happens.
Scientist Stevie,
Yes?
why are the gas particles making the bag expand?
Well, because they want to fill up the empty room here. You know, in space, how there's like nothing there, that's why if you were not to use a suit, all of your gas would be sucked out of you and go into the air. That's why we die in
Would you
space.
say that it has to do with pressure?
Of course it's pressure. It's the pressure in the gas particles going against the bag because they want to fill out the space. Let's turn it on and
To
see
make the
what
pressure
happens.
equal on the inside of the
Let's
bag
go.
and outside of the bag.
Ooh, it's expanding! What will happen? For our second experiment, we'll put this ball inside of here. It does have a little hole in there.
It's
but
not a good idea.
But it's enclosed because the only thing that can penetrate it is the needle. Okay, you ready?
We're gonna.
I'll do it.
Whoa, look at that.
Whoa!
Can we open it?
It's made in China.
Trump. Look, let me.
Whoa! Actually, hold on. See, now, I don't know what's happening here, but I guess some expanded from the inside of here because it is more squishier than it was before.
More
the gas
squishy.
particles have escaped the ball.
Can I see?
You will see.
I assume that the reason that this happened was because it got so blown up that it actually widened the hole here and allowed some air to escape.
Of course.
Now let's look at an example. As we learned before, the equation for Boyle's law is P1 times V1 is equal to P2 times V2. If you have 5.6 liters of gas at 1.5 atmospheres, how much pressure would be required to decrease the volume to 4.8 liters? To find this, we first have to plug in our variables into the equation. The first amount of pressure that we have is 1.5 atmospheres. Our initial volume is 5.6 liters. Then we must have it equal to P2 times V2. So our secondary pressure is unknown. And our secondary volume we know is 4.8 liters. Now we have to solve for x. To do this, you divide by 4.8 liters on both sides. Now you can cancel out the liters, and you would get 1.8 atmospheres for F. Charles's law states that at a fixed amount of pressure and mass, the volume of a gas is directly proportional to its temperature. This basically means that as the temperature of a gas increases, it begins to expand and its volume increases. This law was discovered by Jacques Charles.
Go.
So, Jacques Charles developed an experiment where he put a set volume of gas in different water baths. The gas was under a movable piston, and he noticed that in the hotter water baths, the gas would expand, moving the movable piston up. This proved a direct or proportional relationship between temperature and volume of gas. As the temperature goes up in the volume of gas, the volume does as well.
Go.
Okay, so now to finish this problem up, we simply do cross multiplication, and then we get 330.8 equals 14,400x. So in order to find x, we can just divide it by 14,400, and we get that 0.023 is our x, and that means that it is at 0.02 degrees Kelvin.
Gay-Lussac's law states that the pressure of a gas of a fixed volume and a fixed mass is equal to the temperature. This is a directly proportional relationship between two of the variables. When one of the variables is high, the other one is also high. One of them is low, the other one is low. The equation for this is the initial pressure over the initial temperature is equal to the final pressure over the final temperature. This is Gay-Lussac's law, which states there is a directly proportional relationship between pressure and temperature. Now right here, we have a barometer which is in a cold ice bath here. And we're going to put it on this holding thing over some candles. And then we'll heat it up, and we're going to see the difference between when we do that.
So right now we see that the barometer is in an ice bath, and that the kinetic energy is less than if it were outside the ice bath. So the molecules inside are moving slower, and the pressure out here is different than in here. So to compensate for that, more air is moving into here.
And this is an infrared thermometer. And we're going to see what the degrees of the ice bath right now is. We see it says 35 degrees.
Now we are going to close the valve so that none of the excess air in here can escape when the pressure changes. And now we're going to put it over the candles so the heat will change.
Lussac's law, we can see that this representation of P1 over T1 is equal to P2 over T2. But we can simplify that to an easier expression. P1 times T2 is equal to P2 times T1. Now let's do an example problem here. So if we start off with 4 atm of pressure for the first one, set up with the equation here. 4 atm. And then we also have at a temperature of, let's say, 42 Kelvin. Pretty low, I know. So, but that doesn't work for here, because in this case we need to do the second temperature, which is going to be 20 Kelvin. So right here, times 20 Kelvin is equal to our first one, but we don't know what that is. So we'll put it as X. This will be X atm. And multiply it, as I said before, to the first temperature, which is, again, 42 Kelvin. Okay, right now, we want to get X by itself. How do we do that? Pretty obvious. We can divide by 42 Kelvin on each side. By doing this, divided by 42 Kelvin. 42 here. We can get our answer, but we gotta cross out. So we can cross this one and cross this one. And right here again, cross here. So we just have atmospheres here. So then we have, again, as our final answer, we have x is equal to, plugging this in our calculator, we can get it to 1.9 atmosphere.
Avogadro's law states that when gases are held at a constant temperature and pressure, that the volume and the number of moles will be equal and they are directly proportional. So when the volume is high, so are the moles, and if the volume is low, then the mass will follow.
For this experiment, you will need 2 balloons and some air,
You're going to need one balloon that's pumped with a lot of air,
and 1 balloon that has not so much air. As you can see, the balloon with less gas or less moles of mass has a smaller volume, while the balloon with more moles of gas has a larger volume. This is an example of Avogadro's law.
Okay, so the equation for Avogadro's law is V1 over N1 equals V2 over N2. And if we start with 5 liters of gas that has 0.965 moles, and then afterwards it has 0.18 moles, we're going to be trying to find the volume. So to do so, we're going to multiply across the 5 liters times the 1.8 moles, and then you're going to divide it by the 0.965 moles. And then the moles are going to cancel because you're trying to find volume, so you're going to want your answer to be in liters. So then after you do all of that, then you get 9.327 liters.
Today we learned about how gases aren't just something boring you learned in school. We learned about the variables pressure, mass, temperature, and volume, and the universal gas constant. We also learned about how these variables interact with each other and their relationships, inversely proportional or directly proportional.
Gases are all around us, from the air we breathe to the soda we drink. Even though you can't see it, hear it, or feel it, gases are essential to everyday life. Our unique atmosphere is what makes Earth so special and allows life to flourish. We owe our life to gas.